Let's get started. So I want to welcome everyone to Yu-Hsin Chen's thesis defense, and I'm welcoming you on behalf of myself and as well as Joel Emmer, who is Yu-Hsin's, or co-advising Yu-Hsin's PhD thesis. So Yu-Hsin received his bachelor's degree from the National Taiwan University, and then he got his master's here at MIT, and then he joined me for his PhD degree at MIT. So he is one of the first students who joined my group when I returned. Officially, I checked my emails last night, so he's the official first student by just 1 week. Okay. The other student, graduated or defended last week, so it's a very special week for me because they're both defending at this time. I think Yu-Hsin has the very first journal paper that was published from our group, and also the first chip that was taped up from our group. So another couple of things I just want to mention about his PhD thesis. So Yu-Hsin worked in the area of hardware design for DNNs. As many of you may know, it's a very fast-moving area, so you need to think really deeply in order to make long-lasting contributions in the field. And that is exactly what Yu-Hsin has done over this past 5 years for his PhD. So through his efforts, he has been able to make a strong impact on both the computer architecture community as well as the circuits community. In fact, just for you guys to know, so his work on Eyeriss received a Micro Top Picks Award, and that's from the computer architecture community. And his paper in JSSC is basically the top downloaded paper in 2017 and continues to be so right now. In addition to Eyeriss, Yu-Hsin has also made many contributions to DNN analysis methodologies to really help provide some organization and structure to this really rapidly growing field. So it allows you to gain more insights into the different developments that's going on. And so one example of this is the taxonomy that he's going to talk about in terms of how we describe data flows. And this is widely used now in many of the computer architecture descriptions of DNN accelerators. So with that, we look forward to hearing your talk, and please take it away.
Okay. Thank Vivian so much for the nice introduction. And thank all of you for coming to my talk. And today I'd like to share with you the project I've been working on for the past 4 years. Which is on the architecture design for deep neural network accelerators that's highly flexible and energy efficient. So as we know, nowadays, deep neural nets are used basically everywhere. It's a cornerstone of modern AI systems. It enables applications ranging from smart assistants, self-driving cars, and even to play the game of Go. But what I've noticed is that those new AI applications, they're bringing new challenges to the underlying hardware systems and infrastructure. For example, we need high processing throughput in applications like self-driving cars to deal with a large amount of data. We also need low latency in smart assistants to have a very smooth conversation. In addition, energy efficiency is becoming more and more important because many devices nowadays run on battery. And last but not least, we need the hardware to be very, very flexible because we don't want to just support one net. We want to support many different nets for many different applications. So those challenges have inspired us to propose a new architecture design for DNN acceleration, and we call it Eyeriss. Eyeriss is optimized for the 3 pillars of the architecture: performance, energy efficiency, and flexibility. Specifically, we have designed 2 versions of Eyeriss. The first version, Eyeriss v1, was designed at a time when the DNNs was very large, involved a lot of computation. What we found was that being able to optimize for data reuse is going to be the most important idea. Later on, we proposed Eyeriss v2 because we found that the development of deep neural nets are becoming more diverse. There are large models, there are small models, and we found that there's an issue for those models to utilize the existing hardware. So the idea of the second version is to improve the utilization of the hardware, specifically in terms of the processing elements. So here is a list of our contributions to address those things I just described. I'm not going to go through the list. But one thing that's very important to understand is that, as Vivian said, this is a very fast-moving field with a lot of work going on. And a lot of time you'll feel many of them are a bit ad hoc. So what we're trying to do is to provide a systematic way to analyze this problem. So later on, we can take those methodologies to implement new architectures. Because of time constraint today, I'm only going to focus some key components of our talk for you to take home today. But if you're interested to know more about our work, here's a list of our publications throughout the years. As you can see, we have bridged in both the community of architecture and circuits. And you'll notice in the talk today that we actually do the co-optimization and design all the way from architecture down to the circuit level. So let me first give you a bit of background. So the idea of deep neural nets is trying to use many layers to hierarchically extract meaningful information from the input data. So for example, to recognize the image of the car, at first extract some low-level features like edges, and then gradually put them together to form an object like a car here. Nowadays, the deep neural nets can be very large. They can contain like thousands of layers. And there are many different types of layers that people constantly developing. So we have many different layers. But there's one type of layer that's really fundamental to all different deep neural nets. And that's what we usually call the convolutional or fully connected layer. They account for over 90% to even like 99% of the overall computation, which is why this is really the target layer for acceleration in hardware. So the type of computation that's performed in this type of layer is what we call a high-dimensional convolution. Basically, we start from a 2D convolution in which we apply the filter on top of the input data, which we call the input feature map or Fmap. So this is a really standard 2D convolution. We do element-wise multiplication, and then that will generate a lot of data called partial sums. That's going to be accumulated together to generate just one output value. And then to generate another output value, we do a sliding window processing by sliding the filter onto a different location in the input data. And this only happens in the convolutional layer, so that's the only difference between the conv layer and the fully connected layer. In fully connected layer, the filter size is exactly the same as the input feature map size. So there's no sliding happening here. And as you'll see throughout our talk, we use a consistent color coding for our figures. We use green for filter weights. We'll use blue for input feature map, and we'll use red for output feature map, so you can recognize it better. So in addition to 2D convolutions, there are additional dimensions in the data. For example, we get many input channels in the filter and input feature map. And what we do is to do the 2D convolution channel by channel, and then we have to accumulate the partial sum from all channels together to just generate just one output feature map plane. But in addition, in the same layer, we can get many of those filters. So because each of them will generate one plane here, with many of them, we can generate many of those planes, which we call it many output channels. And at the end, sometimes we can get a batch of data to process. For example, if you have a video stream, right? So we're going to apply the same set of filters on top of each of those input feature maps. And that will generate a batch of output feature maps here. So that's the type of processing we're dealing with here. One thing you'll notice is that there are many different dimensions in the data, right? And unfortunately, they can change from layer to layer, even within the same deep neural nets. So we have a lot of different configuration in terms of number of channels, number of filters. That means we cannot build the hardware to just process one specific configuration. The hardware needs to be able to adapt to different configurations. The second thing you'll notice is that for each layer, there's a lot of processing involved. You usually get from several million to several hundred million of multiply and accumulates. Even though we can use high parallelism, like what we've done in GPUs, to speed up the processing, the actual bottleneck is in how we access data. As you can see here, for each multiply and accumulate units, you have to read 3 pieces of data from memory, and then you need to write the result back to memory. In the worst case, if they all go through DRAM for data access, it will be intolerable. An example here is if we want to support the several hundred million max in AlexNet, we have to do almost 3,000 million DRAM accesses. That's going to greatly impact your performance and also energy efficiency. Luckily, what we can do is we can use some local memory to mitigate this problem. So those local memory can be smaller, but they are faster and more energy efficient to access. So the thing we want to leverage from those local memory is data reuse. What we mean by that is we want to read data from DRAM once to the local memory, and then we use it multiple times from local memory to do the processing in the Mac here. And very fortunately, there are many data reuse opportunity in a DNN. For example, we have the convolutional data reuse, in which case, each filter weight is going to be applied to different locations in the feature map and reused in many different Macs, and vice versa. We also have feature map reuse, in which case, the same activation is going to be used across many different filters. And similarly, we also have filter reuse, in which case the same filter weights is going to be applied on many different feature maps. So if we can actually leverage all those data reuse opportunities, in the case of AlexNet, we can actually reduce the 3,000 million accesses to just around 60 million. That's around 50 times reduction. And that's going to help the performance and energy efficiency a lot. But this is only about how we leverage data reuse through the memory. And there's actually another opportunity here. Remember that we can use high parallelism to achieve high performance. Basically, we can supply a lot of those compute data paths here. What we can further do is to exploit what we call spatial data reuse with the parallelism. What that means is we just read the data, for example, the weights here once from the memory, and then we broadcast that to many different compute units. So we also reduce the memory access through the local memory. So now we know there are two properties we like. We want to have local memories for data reuse. We want to have parallelism not just for higher performance, but also for data reuse as well. That is why spatial architecture is a very popular architecture that's being used in many of those specialized hardware you'll see nowadays. The spatial architecture, first of all, it's a highly parallel architecture. You can get from hundreds to thousands of those ALU for processing. And also, it supplies some local memories. For example, we have the register file for each ALU. And together with some control logic, we call this a processing element. And also, we can have some global buffer that can supply data to the array of processing elements. And then we can also further customize the on-chip network that delivers data between the global buffer and the PEs, so we can get high reuse from that as well. So suppose today we want to run the operation of a Mac on a specific ALU. We have a lot of choices in the architecture to fetch data from. We can fetch data from the local register file. We can fetch data from a neighbor PE, or even from the global buffer, or even the remote DRAM as well. What we've noticed is that accessing data from different places actually incur different energy costs. For example, accessing data from DRAM is going to be orders of magnitude higher energy consuming than the accessing data from the register file. So what we'd like to do is we'd like to maximize data reuse in the register file, and then we can minimize the data access to DRAM. And what this involves is to construct something called a data flow. A data flow basically is a rule saying how you like to order the operations both in the time domain and both in different PEs as well. So if you can find a clever way to do that, then you can exploit data reuse in those low-cost memories and also with the parallelism you have. And this is a very hard problem because, first of all, the neural nets are very large nowadays. And we usually have a limited amount of local storage, like register files or number of PEs. So how do we find a way to achieve a high amount of data reuse, and at the same time being able to adapt to different configurations of the layer, that becomes a really important question to answer. And there are actually a lot of work in the field that's trying to answer this question, and we are trying to gain some insight into how they do it. And throughout our research, we actually found that despite their different design trade-offs and implementations, we can categorize most of the work into just 3 major data flow categories. The first data flow is what we called a weight stationary data flow. The idea is that we want to read each weight just once from the DRAM and put it into the register file, and then you access all the future data from the register file. By doing so, you minimize the rate reuse, or the weight accesses, because you always access data from the register file. And there are actually a lot of work that do this type of data flow, and most notably, probably the Google TPU also can be categorized into this category. And the second data flow is called a output stationary. Similar to weight stationary, the output stationary is trying to minimize the data access of data energy consumption of accessing partial sums. So for all the read and write of the partial sum, you are going to do that through the local register file instead of pushing it out back to the global buffer or DRAM. And as we can see, there are also many different implementations that use output stationary data flow, and actually they're very popular in some recent year publications. And the last data flow is what we call a no local reuse data flow. It's different from the previous 2 in that there's no local register file in the PE. So what you do is you read the data from the global buffer, you do the computation in the PE, and then you just push it back to other PEs or back to the global buffer. So what it does is that it trades off the area for a lot of local smaller register file for a much larger global buffer here. And that's good for fetching a lot of data at a time from DRAM to the chip. So you minimize the access to DRAM. As we can see, there are also a bunch of different work that work on use the no local reuse data flow. So after we examine those 3 different data flows, we actually found that it's possible for us to build a new one. We called it row stationary data flow that can further optimize for energy efficiency. The idea is that we want to maximize data reuse through the register file, but we don't want to do that just for a specific data type. We want to optimize for the overall system energy efficiency. So here's how we do it. We'll start from a simple 1D convolution, and we'll build it up to the full high-dimensional one. Let's say we have this 2D case here. We will first just fetch 1 row of filter weights and 1 row of input feature map to do the 1D convolution that will generate the partial sum for just the first row of outputs. And we'll do this first row inside the same PE through the register file here. So first of all, we fetch the filter row into the register file, and we fetch the first window of the feature map into the register file as well. And then we run through 3 cycles of multiply and accumulate. That will always accumulate on top of the same output A here. So you almost always accumulate that in the register file. Then you move on to the next sliding window. What we see here is that we can further reuse the same filter weights here in the register file for the next round of processing. But we also reuse part of the input feature map by replacing A with D here. So you also get some reuse from that. And you can do this on and on until you're complete with the processing. What this does is that you actually maximize the amount of reuse for all 3 data types in this 1D convolution at the register file level. So now we know how to do a 1D convolution. We'll build it up with a 2D convolution. So first of all, we take 1 PE to run just the first row of 1D convolution. But in order to complete the processing of the first row, we need other rows as well. So we further take a few more PEs, like 2 more, to run the other row combinations. And each of them will generate the partial sums that need to be further accumulated together. What we do is to simply pass them through the P array to do accumulation without pushing them back to the global buffer. So we can accumulate that directly in the P array to complete the processing of the first row. And in order to complete other rows, we simply take more PEs. So it reuses the same weights here, but we have the shifted version of the input, like from row 2 to 4 instead of 1 to 3. And that will complete this row second. And we can also do this on and on until we're done with the entire 2D convolution. And what this does is that, remember, we can leverage spatial data reuse with parallelism. And you can see that we actually reuse the same row of weights horizontally across the different PEs in a row. So we can leverage spatial data reuse there. The same thing happens for input feature map. Now we reuse them diagonally through the PEs. So we can also have spatial reuse there. More importantly, for the accumulation of partial sums, that's also done directly inside the P array without involving the global buffer. So that also maximizes the amount of accumulation we can do inside the P array. So that's how we complete the 2D convolution. But there are also many more dimensions we have to complete, right? So that's where the flexibility kicks in. Let's say we have many more feature maps to process. We can simply run through many feature maps inside the same PE with the filter we have there. So we further get more reuse of the filters. And the same thing happens when we have more filter weights or more channels. So basically, we can find out a way to see how many different feature maps or filters or channels we want to put on the same PE for processing, so we can optimize for data reuse. And this becomes an optimization problem. So that's why we build an actual compiler to do this optimization. It takes in the specific layer shape of the DNN, and it takes in how much memory you have and how many PEs you have here. It can figure out what's the best way to do the mapping so it can optimize the energy efficiency. And overall, you get a mapping that you can run, and that's energy efficient. So with that, now we can compare our row session in Dataflow against other existing ones. We do this simulation assuming the same amount of total area across all data flows. They also have the same number of PEs. And we use AlexNet layer configuration for this simulation with a batch size of 16. So first of all, we compare the different data flows in the x-axis here. And in the y-axis, we have the energy normalized to each MAC operation. The first thing you'll notice here is that for all different data flows, they all have the same amount of ALU energy consumption because they all run through the same amount of operations. And what's really defining the final energy consumption is how they access data from the memory. And as here we can see, row session is only one that has the most data access to the register file. In the end, has the most energy consumption in the register file, but that helps us to minimize the overall energy consumption. And one example that's interesting to point out is the no local reuse one. It actually minimized the amount of DRAM accesses, but in the end, it still put a lot of access to global buffer, and that's not going to optimize for the overall energy efficiency. And that is why our row session in Dataflow can get 1.4 to 2.5 times lower energy than the other data flows.
I have a question. What is the relative access and power difference between global buffer and DRAM?
Yeah, so we showed that in the earlier slide. Basically, we profile from a real technology, the 65 nanometer technology. So we assume that for register file, access to that account for like 1 unit of energy. But for NOC, that's around 2. For global buffer, that's around 6. And for DRAM, that's around 200. So there's a hierarchy of different energy cost. And what we do is trying to, with this cost, how to optimize the data access to each different levels. Okay. So here is the same data, but we present it not in terms of the breakdown in different hardware components, but we break it down in terms of different data types. So for weight station data flow, it's clearly showing that it has the lowest energy consumption for accessing weights. For a different variation of output station data flows, it has the lowest energy consumption for accessing outputs. But again, the row station data flow is the one that optimizes for the overall energy efficiency, and that's why it gets the best results. So with the row station data flow, we build an actual architecture called Eyeriss v1 to support that. First of all, it used row station data flow to optimize for data reuse, as what we just saw. It has more features, like we use a very flexible mapping to improve the P utilization. We also leverage the sparsity, the data, to reduce the processing power and reduce the amount of DRAM traffic further. So here's a top-level block diagram of our Eyeriss v1 architecture. On the right, you can see we have a 12 by 14 array of processing elements. And they can talk to the global buffer here in the middle, that's around 100 kilobytes, through some on-chip network. The global buffer can talk to the off-chip DRAM through some data buses. And you'll notice that there are some components here that's doing compression and decompression, which we'll talk about in a minute. So the first question we have is that the row station data flow actually map the data in a very specific pattern. So we want to have the number of rows of PE equals to the filter size. We want to have the number of columns for PEs equal to the output feature map size. But now we have a fixed size of 12 by 14 array. How can we map different shapes onto the fixed P array? So we developed some very flexible mapping strategy to deal with this problem. The first strategy is called replication. Here, to give you an example, in AlexNet layer 3 to 5, the filter size is 3 by 3, and the output feature map size is 13 by 13. That results in a 3 by 13 P array that we like to use. That is much smaller than the physical P array we have here, which is 12 by 14. So what we do is simply replicate this structure 4 times to fill the P array. And we can run through different feature maps or filters in different replications, so we get higher performance. The second technique we use is called folding. So one example here is the second layer of the AlexNet, which require a 5 by 27 P array. That's much wider than the 12 by 14 we have here. So what we do is we can cut it into half and fold it on top of the 12 by 14 P array, so we can still run through the processing without sacrificing the performance. So now we know how to map the operation on top of our architecture. The next natural question is, how do we deliver data to them? Specifically, because of our data flow, we have patterns like delivering filters horizontally, delivering the feature maps diagonally. The simple solution is to simply broadcast the data to all the PEs and let the PE decide if you want to take the data or not. But that's going to be very energy consuming from our experimentation. So what we developed is actually called a multicast network. Basically what it does is, if you know you're only going to send data to those PE on a row, you can shut down the data bus in the other rows. And that similarly can happen for filter weights, feature map here. So by doing so, we can still provide any data delivery pattern, but at the same time, we save over 80% of the energy by doing a simple broadcast. And something we notice in the data is that there are a lot of natural zeros in the feature map. So we also want to exploit that property. And since we know if the data is 0, you do multiply and accumulate, that will still result in 0. So you don't actually need to do the processing. So what we do is, when we encounter a 0 in the PE, we simply shut down the PE for that cycle. So you don't have any switching power. In that case, we can save over 45% of the PE power with this type of simple logic. And the next thing we can do is we can actually leverage those zeros to do compression. And we use a very lightweight compression to make the data traffic through DRAM much smaller. So as we can see here, we can get 1.2 to even 1.9 times fewer traffic to go to DRAM. So with all those features, we tape out the Eyeriss V1 architecture into a real chip. It's fabricated in a 65 nanometer process. And we do a measurement, and what we see was that we can achieve around 35 frames per second performance for the convolutional layers of AlexNet at around lower than 300 milliwatts. More importantly, to support those processing, which involve around 16 gigabytes of raw inputs and 4.5 gigabytes of raw outputs, we only need to access the global buffer and around 200 megabytes, and then DRAM for around only 15 megabytes. So here is a quick comparison between the Eyeriss V1 chip to a leading GPU at the time of this measurement, which is around late 2015. So the two architectures, they use a similar amount of resources, while the GPU uses a much more advanced process. But what we can still achieve is around 10 times higher energy efficiency and a much lower access to DRAM. So now I'm going to show you, yeah.
This comparison with the GPU, you're doing a single SM, not the whole GPU?
It's a whole GPU.
Okay.
Yeah, this is a small like mobile GPU. Yes. So we further take our chip and integrate it into a real hardware system to do a actual real-world application for image classification. What we do here is we fetch any image from any places, like in this case, a dog image, and then we're going to send this image to our system for processing. So what you'll see is now the image is being sent to our Eyeriss chip, and it's doing this deep neural net processing on the chip here, and then they send it back and says it actually classified that as a dog. What this shows is the capability of the chip to be flexible enough to support real-world applications. So to summarize our work on Eyeriss V1, first of all, we propose a taxonomy of data flows that involve three major categories of data flow to categorize existing work. That's going to provide you insight into understanding different works. And with that, we further propose a new data flow called row stationary. The idea is to optimize for the overall system energy efficiency, which is why we can get around 1.4 to 2.5 times higher energy efficiency than other existing data flows. And with that, we propose our Eyeriss V1 architecture. It uses the row stationary data flow to be very flexible and energy efficient in terms of optimizing data reuse. We leverage sparsity in the data to reduce PE power and reduce DRAM traffic, so it's more energy efficient. We also use a very flexible mapping scheme to improve the utilization of the processing elements. So it's also flexible and improved performance. And last, we implement a network that can support any delivery patterns, so it's flexible, but at the same time, it's not energy consuming as a broadcast design. So we also improve the energy efficiency in the design. Overall, it translates to over 10 times higher energy efficiency than a mobile GPU. And we also further demonstrated a real image classification system with our chip to demonstrate the flexibility.
So this row stationary idea, which I didn't completely understand, can it be applied to GPU programming also?
So the question is, can we apply the row stationary data flow to a GPU architecture? So the idea of the row stationary is that you need to have the hardware that can actually leverage the potential of the row stationary data flow. So the GPU architecture is not necessarily to design for exploiting data reuse. So for example, we need to have specialized network and we need to have like local storage that's low cost enough to actually leverage those potentials.
But a central idea I thought was that you're making better use of the data, right, in the local storage. And even that idea is not easily translatable into GPU's architecture.
So I think it's really important to have a co-design between the data flow and the hardware to actually leverage its full potential. Yeah. So after we've done with Eyeriss V1, we actually noticed that the field is moving at a very fast pace. So we actually have done some serious survey in terms of what's happening in the field, and we put those knowledge into a preceding paper here on efficient processing of DNNs. And through this process, we actually recognize some limitations to many of those existing approaches to design. Specifically, what we notice is that the deep neural nets nowadays, they're becoming more and more compact. Through the idea like filter decomposition, we break down the large filters into many smaller ones, or like bottleneck layers to reduce the complexity, we can make the network more compact. For example, one net is called MobileNet that's proposed last year. It has actually higher accuracy than AlexNet, but at a much lower number of weights and amount of computation. But the question is, does that translate to higher performance in the hardware? I think one thing we keep saying today is data reuse. We want to have data reuse to get better performance. So we examine the data reuse in those neural nets. And unfortunately, it's actually going against our favor. What we're showing here is 3 different nets throughout the years of development. So toward this direction, we actually get more and more of those compact features. On the y-axis, we have the amount of data reuse, basically saying how much MAC operation that each data can support. And this is showing for the input feature map. For each data point, that shows the data reuse for one specific layer in that net. And we have a red point that shows the median value of the data reuse in the same net. Across the 3 nets here, you'll see that the average amount of data reuse is actually going down. And another thing is the variation in data reuse is going up in neural nets. That means we have to deal with not just the low amount of data reuse, but a wide range of data reuse in the architecture. So what does that mean to our hardware performance? Here, I'm going to show you one simple example to illustrate that. Suppose our hardware is built to exploit reuse for weights. So we have 4 PEs. We send out the same weights to 4 PEs to do processing with different feature maps. Suppose today we don't have enough reuse. Let's say for each weight, we can only reuse that with 2 different inputs instead of 4. In the first case, if the data flow is not flexible enough to actually schedule other operations on those 2 PEs, you have idle ones that hurt your performance. But in the second case, even if you have a flexible data flow to schedule out the operations, let's say we schedule not all W1, but W2 for the other 2 PEs. Because we only have a broadcast network here, that means we have to send W1 in one cycle and W2 in another cycle. So we don't have enough bandwidth to provide the data either. That also hurts our performance. So overall, if we don't have enough reuse, in some existing designs, the performance will go down. So our idea is, in order to mitigate this, we need to have a very flexible mapping strategy. It involves 2 things. First of all, we need to have a data flow that's flexible enough to avoid idle PEs. But at the same time, we need to improve the design of the network to deliver data so we can exploit data reuse. But at the same time, we can provide enough bandwidth. Specifically, there are those 3 different cases we like to support. For example, when we can get a lot of reuse for weights, we can send the data to different PEs to get data reuse with different inputs. But when we don't have that much reuse, then we can get more weights to do the processing to fill other PEs. And then in the ultimate case that we just don't have reuse for weights, then we want to be able to provide enough bandwidth to supply the processing to keep up the performance. So what you'll notice is that there are 4 very specific delivery patterns of the data. We want to have unicast for delivering high bandwidth. We want to have broadcast to support high data reuse. We also want to have something in the middle, like for broadcast, for multicast. So we have grouped multicast here. We multicast in different groups. We have interleaved multicast here as well. So they all come in pairs. So if you have unicast in one data type, then you have broadcast for the other. If you have multicast in interleaved fashion, then you need to have the group multicast for the other as well. The question is, do we need all of them for our architecture? So let's take a look at how we deliver our data, specifically input feature map in the row stationary data flow. First of all, I'm going to show you the case in AlexNet, and I'm showing 2 charts. This one is how we deliver data horizontally in the P array, and this one is how we deliver data vertically in the P array. Each pie chart is showing that how much data is actually being delivered at the specific fashion, either unicast, multicast, or broadcast. As you can see here, all 3 types of data delivery are heavily exercised in amount of different layers in the same neural nets. Furthermore, we also have the result for mobile nets. As you can see, because the amount of data reuse is less in MobileNet, so we actually have to do more unicast in this case. But overall, all 3 types of data delivery, they are still very important to optimize for performance and energy efficiency. So we need to be able to support all of that. So one goal in our design of Eyeriss v2 is we want to be able to support a wide range of data reuse. If we have a high amount of data reuse, we can leverage the idea we proposed before to exploit them. But when we don't have enough data reuse, what we want to have is the data flow that's flexible enough to minimize the number of idle PEs. And we also need to have the network on chip that can provide high enough bandwidth. Specifically, we need to cover all different delivery patterns. So the second thing we've noticed from the network nowadays is that they actually can be pruned a lot. That means in one case that's developed in our lab is we prune the AlexNet. So we can still get similar accuracy, but at a much lower number of weights and computation compared to the dense one. And we want to be able to leverage that for better performance and energy efficiency. So the second goal in our second version of Eyeriss design is being able to support a wide range of data sparsity. Specifically, we want to leverage the sparse feature maps and weights and translate that to higher performance and energy efficiency. But due to the time constraint today, I'm going to focus only on how to support a wide range of data reuse in this talk. So first of all, we want to improve our data flow. As you remember, we have a data flow that's very good at exploiting data reuse. The thing we want to further improve is how do we minimize the number of idle PEs. So there are 2 main ideas we propose here. The first one is we want to be able to map data from different dimensions, and actually from all different dimensions to different PEs. For example, in this case here, if we have many input channels, we can actually map data from different input channels on top of one specific dimension of the P array. But in the case when we don't have input channels, we don't want to waste the PE array to do nothing. So we can replace that with another different data dimension. For example, different columns of feature maps to further fill the P array. And the second idea of this data flow is that we want to be able to map not just one, but multiple dimensions of data onto the P array at the same time. So for example, we can break the P array down into blocks. For each block, we can map data from a set of different dimensions. And then at the block level, we can mix and match another set of dimension. So by doing so, you have a lot of flexibility to choose which data from which dimensions you want to map at the same time. And so overall, you can maximize the amount of utilization of the PEs. So by doing so, this new data flow, which we called it Row Stationary Plus, it can minimize the number of idle PEs, so you can get higher performance. At the same time, it's actually a superset of the row stationary data flow, meaning that all the mapping that row stationary can do, the Row Stationary Plus can also do as well. So you always get the same or even better performance out of it. So now data flow is not an issue anymore. The next bottleneck becomes the on-chip network design. So here I list out 3 common designs among existing work. First of all, we have broadcast network. So even though we say the Eyeriss V1 network is a multicast one, in terms of the source bandwidth, it's still the same as a broadcast network. So in this network, you get high reuse, but you don't get high bandwidth from the source. Alternative is you can do unicast network, in which case each one gets own data source. You get a much higher source bandwidth from this one, but you really don't get much reuse. So to get the best out of both worlds, we can have this all-to-all connection, which you can leverage both high reuse and high bandwidth at the same time. But as you can imagine, the cost of this will grow quadratically with the size, which is really hard to scale in real implementation. So something we remember from our architecture class is that mesh network can be a good solution to this. So what we do is, in between the source and destinations, we use routers to connect them in a linear fashion. So it can easily support high bandwidth modes. It can also support high reuse mode by using a router to send data to everywhere. But in some more complicated cases here, for the group multicast, we can still support that by separating them into disjointed sections. However, for the interleaved multicast mode, we have issues supporting that because in the case here, we have a bandwidth limiting route. You either have to suffer for lower performance, or you need to implement some flow control logic that's going to make the cost higher. So both ways, we don't like that. That's why we propose a new design called a hierarchical mesh network. The idea is that we want to be able to support a wide range of data delivery patterns. At the same time, we want the cost to be low so we can easily scale the size. This is the idea of the hierarchical mesh network. Basically, in this case, we group 2 sources into a cluster, 2 routers into a cluster, and 2 destinations into a cluster. So between the clusters, we use the simple mesh network to connect them. And within the same cluster, we use the all-to-all network to provide enough connectivity. But since the cluster size is usually much smaller than the full size of the array, the complexity can be well contained. So now we can support high bandwidth mode fairly easily. We can also support high reuse mode by sending data from one source to all destinations. For grouped multicast, we can leverage different clusters to do different groups. And then for the interleaved multicast mode, we can leverage the higher bandwidth between the clusters to deliver the data as well. And this is a case where we interleave in the number of 2. If you want to interleave more, you can simply scale up the cluster size. Another thing I want to point out is that all the routing can be done at configuration time. So you don't need to figure out where the data want to go at the runtime. That means the implementation of the router can be simply a circuit switch design. They contain only muxes. They're really cheap to implement. So in terms of the scalability of this design, first of all, we determine the size of each cluster based on how much you want to interleave the data and what's a tolerable cost you can tolerate in this all-to-all connection. And then with that cluster, you can simply scale that linearly. So the cost will scale also linearly. And compared to an all-to-all design, the cost will scale at a much greater level. So with this idea, we propose our Eyeriss v2 architecture. This is a more distributed architecture. As you can see, for the sources, we have our global buffer cluster. For our destinations, we have our PE clusters. And they are connected through the router clusters in a mesh fashion. So some typical numbers we use in this architecture. For a global buffer cluster, each one is around like 10, 11 kilobytes. For the PE cluster, what we use is normally around like a 4x4 P array. And at this type of configuration, what we see is that the network only consumes around 3 to 5% of the total energy. This is a very low cost, and you can imagine when you scale up the architecture, the ratio will roughly stay the same. We compare this to an all-to-all network, which the cost will scale quadratically. This is clearly a more economical and efficient design. So with this new network architecture, we've done some simulation to compare what's the actual benefit in terms of throughput. And we compared that to our old design, Eyeriss v1. For this simulation, both designs have 256 PEs. In v1, that's a simply 16 by 16 P array. But in v2, we have 16 clusters, each with 16 PEs. And we use batch size of 1 to exercise a lot of those corner cases. So first of all, this is the throughput speed up from Eyeriss v1 to Eyeriss v2 in AlexNet. So remember that AlexNet is actually a very large net. So it actually has a lot of data reuse in the convolutional layers. So we don't get really much improvement, like 1.5 to 2 times improvement in throughput for convolutional layers. But the benefit really kicks in when we run the fully connected layer here, because in batch size 1, the weight has absolutely no reuse at all. And that means we need to provide really high bandwidth to supply the weights. And V1 simply cannot afford that. And that's why we can get much higher improvement in throughput. Another net we ran is the MobileNet, which is a much more compact design. As you can see, even though in convolutional layers, because it's a more compact design, we constantly get a much higher improvement in throughput. That's around 3 to 5% at least. And in some layers, we can also get a much higher throughput speed up because those are the depth-wise convolutional layers in MobileNets. They have no input channels, they have no output channels. That means you need a really high bandwidth to deliver the input feature maps, and V1 also cannot keep up with that. And that's where V2 actually get a much higher throughput improvement. So overall, we average the amount of improvement across different networks. And at the 256 PEs, we constantly get around 10 times or more speed up than V1. But when we scale up the number of PEs, we can see that the number of speed up also increased much more. That's because the bandwidth of V1 simply doesn't scale. And we have a much scalable design for V2. So overall, we get at least 10 times speed up than V1. So to summarize what we've done in V2, first of all, we want to support a wide range of data reuse. We've done that through a new data flow called Row Stationary Plus to minimize the number of idle PEs. And then we propose a new network called Hierarchical Mesh Network that's going to provide high bandwidth and also exploit data reuse. So overall, that translates to over 10 times speed up than Eyeriss v1. The second thing we didn't have time to talk about today is how to support a wide range of data sparsity. The basic idea is that we can process both feature maps and weights in the compressed format directly, and that can help us to improve throughput and energy efficiency. But we can also adapt when there's no sparsity. We can process the data directly in the raw format, so we don't incur the compression overhead. And from that, we see at least additional 3 times speed up from sparsity as well. So that summarizes Eyeriss v2. And to conclude my talk, we know that processing of deep neural nets is going to become more and more important because we're going to use it more in our lives. And one thing we've recognized is that being able to optimize for data reuse is the key to achieving high energy efficiency. In order to achieve high performance, we need to be able to have a high utilization of the processing elements. At the same time, we need a network that can deliver the data. And we need to do all this in a very flexible manner because we have to support a wide range of different neural nets, and also they are constantly evolving. And this can be done through the co-design of what you see here today, Dataflow and hardware. And then we can optimize for the 3 pillars, the performance, energy efficiency, and flexibility. Overall, if we can achieve this balance, that can open up new opportunities for AI applications in the future. So that concludes my talk. And I want to acknowledge a lot of people that carried me through this project. So first of all, my advisors, Vivian and Joe. I think being able to participate in the Eyeriss project was truly an amazing journey. Like from day one, they've been so devoted in this project, and that's what pushed me through the project. And most importantly, I think they're always having like the most confidence in me that I never have. So that's how I can carry through this project and done something I could never have done without them. And so I really want to acknowledge that. And also, I want to thank my committee member, Daniel. I know this is a very busy time for you, and very thank you to serving on my committee. And thank you for your feedback for our ISCA paper as well. As you can see, I want to thank our collaborator, Tushar here. He basically came up with the idea of the network in Eyeriss v1 like 1 month before our tape out. So without him, we cannot have the chip done. So next, I want to thank all the members in our EMS group. I think I'm very lucky to see how the group getting stronger every year with all like great people from you. And I think the other thing I'm always surprised is like how well we complement each other in terms of our expertise and how well we have different like experiences. So I really want to thank all of you guys. And the most important in my life is probably my wife, Sasha. I'm all alive and kicking today like because of her. And like I always work in weird hours. I have a lot of weird constraints. And I really thank her for accommodating all of that.
That's done now, by the way.
Yeah, hopefully. And in the end, I want to acknowledge all my friends and family. I think they're very essential in my life at MIT to make them fuller and make them more meaningful. So I want to thank all of them. So that concludes my talk. I'm happy to take questions. Thank you.
Put this into perspective a little bit of sort of what you think the future will hold. So if you think about, we're making these calculations more and more efficient, but there's some theoretical limit. Where are the opportunities for big improvements in the future, and how much opportunity is there for?
So I think so the question is, what are the future opportunities we can leverage from our knowledge, right? So I think one thing we've noticed is that we have a knowledge in terms of how we like to see the hardware evolving, but not necessarily the network are doing in that way. So we want to translate our knowledge in hardware back to how to do the network design. So together, I think they have a great opportunity to further improve all the performance, energy efficiency down, maybe in another even order. So I think there's a great opportunity there as well.
You talked about the compiler of it for the Eyeriss version 1, but how about Eyeriss 2? Are you able to build a compiler for that kind of architecture?
So basically, we can leverage a similar idea from Eyeriss v1 to build a compiler for Eyeriss v2 as well. But now we can actually incorporate more constraints, like not just for energy efficiency, but also for performance as well. And depending on how you like to optimize for two different things, you can build a compiler for that.
Okay, so you don't have it.
Oh, we have it actually. Yeah.
It's very related to the first question.
It seems possible that the trend towards more compact networks with less reuse is actually driven by the hardware of today, which is really bad at reuse. But if you had if you had your Eyeriss v1 10 years ago, maybe that wouldn't have happened even. Networks would be more regular and easier to implement.
Yep.
Do you see is there likely to be a better kind of network that can emerge from your hardware and yourself, and you see where it's going?
I think yes. I think the answer is yes. So what that's happening is because like most of the hardware used nowadays are like GPUs and CPUs. They don't necessarily can exploit like the data reuse we've talked about here. But nowadays, like a lot of people are working on like custom hardwares, and you're going to see more and more people using that. And apparently, that's going to propel like the development of the neural net as well. So I think that takes time, but I think that will happen in the future.
Is there a specific aspect of next generation networks that you might imagine becoming stronger?
So we all like to see like it becomes smaller, like with fewer weights and less computation. But if we can do that in a way that's not really detrimental in terms of how we do data reuse, because that's really fundamental how we can achieve a really good energy efficiency. So we can achieve both at the same time. I think that would be really great.
So related to that, have you given some thought about what a good benchmark would be for if you analyze the network? What simple or maybe complicated computation can you do to figure out how efficient this thing can run?
Yeah, that's a good question. So we actually, the question is, what's a benchmark we want to use to effectively evaluate different architectures? Does that capture the question?
The neural network architecture.
Yeah, so that's actually our long-term question throughout the years. And we actually try to advocate for people to use a more complete set of benchmark to evaluate different architectures, so you don't just look at one aspect. And what we've seen is that certainly you want to evaluate on a wide range of set of different neural nets that people use a lot. And certainly what we've identified is that there are certain corner cases like depth-wise layers, fully connected layers, they all have very different characteristics. And I think it's very important to test across a wide range of different configurations in terms of the shape and size of the DNN layers in order to get a full idea of how the hardware performs. Yeah.
So you talked about row-stationary data flow, and I wanted to get your sort of insight on, there's been a lot of work on HPC and regular also applications into hierarchical tiling and trying to exploit reuse at different levels of the memory hierarchy. So there's things like polyhedral compilers.
Yeah.
How does that relate? How do these insights relate with this broader class?
Yeah, so the question is, there are a lot of existing techniques like polyhedral model in the contemporary compilers that try to also improve data reuse in different algorithms. How do they relate to this kind of work, right? So I actually looked into polyhedral compiler at the very beginning of my research. What we found was that polyhedral compiler, first of all, they target very specific. They work on very specific architecture. You run the compiler when you know what the architecture will look like. But even with that, first of all, that's still a large space to search. That's actually 8-dimensional space. That's a lot of space to search for. And furthermore, if you can actually co-design the hardware, that open up infinite opportunities. So what we really want to do is get some insight into how we can actually do this well.
So once you have the hardware, could you use these polyhedral compilation techniques?
So if you know exactly how the hardware will perform, Like if you know like I just use this CPU architecture, then you can build a polyhedral compiler for that specific setting. But now since we have the opportunity, we open up the opportunity to even co-design the hardware. That means that we cannot simply just apply this. We don't even have what type of architecture we want to run this on, right? Yep.
You want a follow-up question?
Yeah.
I'm still not very clear on, once you have the architecture, what are the differences, right? Like you mentioned, well, the difference is that we open up the architecture, right?
Yeah.
Now you have come up with an architecture, right? So in
Yes.
terms of doing the mapping.
So you can somehow think of that. Oh, the question is, if now we come up with architecture, can we utilize the idea for the polyhedral model? I think our compiler is actually doing a similar thing to what the polyhedral model is doing, basically. And that's for our architecture, right?
Yeah, you talked about some sparsity in design. I was wondering, can you give some highlights? What's a new challenge if there's some sparsity, either in the data or in the neural network?
Okay, so yeah, the question is there anything special I'd like to talk about in how we design the sparse architecture? Yeah. So it's actually a co-design, like in terms of a collaboration between me and a group member, Dan in our group. So we have a model to actually prune the model, the network model, so that can run very energy efficiently on the hardware. So it's not like you prune the model to target just the fewest number of weights, but we want to prune in a way that it can run nice on top of our hardware. And then our hardware, basically, it's a new design of the processing elements that can take in the compressed format of the weights and feature map directly. So when you do this type of processing, you can skip the zeros cycle directly. So you can improve the energy efficiency and processing throughput. That's basically like the high-level idea of this design.
Any other questions? Final question?
Are there any tricks in the actual hardware synthesis that can help with energy efficiency here? Did you use anything? Or is it just kind of compile the RTL? Did you have to babysit it to get things located spatially where you wanted them?
We didn't, so the question is, did we do any special tricks in terms of the backend flow to make it better? So we didn't really look into that direction, so we use a pretty standard digital flow. I think there's a lot of opportunity in terms of how you can further tweak the circuit down. Like I think those are the optimization we didn't really look into during the time, yeah. Okay.
Any more?
So this is all focused on neural networks, but in designing this architecture, have you encountered other applications that these techniques could be good at? Right? Are there other problems in other domains that you could leverage this type of techniques?
Yes, the question is, are there other type of problems we can leverage this type of architecture? I didn't actively look into other problems to solve with this architecture, but I think something similar, like people are trying to solve like graph problems. I think there are opportunities. Like there's also sparsity in the data. You can leverage similar ideas. Other than that, I didn't really have much, but I think graph is some possible applications.
Okay, well, let's thank Yu-Hsin again, and we'll close the open